Hello and welcome to the HPC on AWS webinar. My name is Francesco Ruffino and I am an HPC specialized solution architect. So this is the agenda for the webinar today. We will start describing why it makes sense to run your HPC workload on AWS. Then we will describe all the available technologies on AWS and how to use them and how to choose the right configuration for your workload. And lastly, we'll show some use cases and example. You can now enter your questions and I will try to answer at the end of the webinar. So let's start with the why. Why makes sense to run HPC on AWS? The main reason is it's because this will help you to innovate faster. The demand for HPC workload is very variable. So it's difficult to match a variable demand to static on-prem infrastructure. On the contrary, on AWS, you have access to virtual unlimited infrastructure, and this allows you to scale on demand very quickly, and you will only pay for what you use. On the contrary, on-prem, you are limited to the fixed side of your cluster. So if you need, for example, to move from 100 nodes to 1,000 nodes, you can do it immediately on AWS. But on-prem, it will take you probably months to provision these new instances, these new nodes. And because you are only paying for what you use, you are sure that you are optimizing also your spending. Finally, with our global footprint, you can increase collaboration and access your HPC cluster all around the world. And so this results to faster time to result and a better return on investment. So we mentioned before the global collaboration. The AWS cloud is distributed all over the world. We have at the moment 18 regions and 55 availability zones. Here in this slide, you see this bullet, or every bullet is an available zone, and the number inside is every bullet is a region, and every and the number indicates the number of availability zone inside the region. We have also announced 4 more regions, one in Bahrain, in Hong Kong, in Sweden, and second AWS Gulf Cloud region in the US. So another reason is the cost advantage. On-prem, you need to deal with a very high upfront capital cost, and also the procurement process can be expensive and time-consuming. On the contrary, on AWS, you can pay only for the resources that you need and when you need them. For example, when a new instance type becomes available, you can immediately test your application and then switch to the new instance type, improving performance and reducing your cost immediately. So the users don't have to wait for the next technological refresh to start benefit from an hardware upgrade. We will see in a minute that you can also benefit from different pricing model. And finally, you can move from a CapEx to an OpEx model that can be convenient for some organization. As we mentioned before, we have several different purchasing options in AWS. These 3 are the most popular, I would say. On-demand is our classic approach. With on-demand instances, you pay only for the resources that you need when you need them, without any long-term commitment. So on-demand is really perfect for spiky workloads. If you can make 1 or 3 year commitment, then you can use reserved instances, and you can receive a significant discount compared to on-demand. Finally, we have spot instances. Spot instances offer spare compute capacity that is available in the AWS cloud for a very low price. You can save up to 90% in comparison to the on-demand price. The spot instance price is set by Amazon and is adjusted gradually based on long-term trends in demand for spot instances and capacity. When AWS needs the capacity back, spot instances can be interrupted with 2 minutes of notification. So it's very important to use spot instances only for application that can be interrupted and resumed. Anyway, you can always use a spot block for if you want to, let's say, if you know that you have to keep your instance for a predefined duration, you can use a spot block and you can keep it for hourly increment between 1 hour and 6 hours. And this will give you a discount that is in the range of 30–50%. So you can use spot instances for jobs that can be interrupted and resumed. You can use reserved instances if you can express a 1 or 2 year commitment. So reserved, for example, can be very useful for nodes that you always have to keep up and running. For example, management nodes or license nodes. For all the other type of workload, you can use on demand. And you can also combine these 3 different models in order to tune your spending. Now let's go to the next topic. So what are the components of an HPC solution on AWS? So we have different tools and products that you can use. Obviously, the center of running your HPC workload on AWS is EC2, the Elastic Compute Cloud. EC2 instances are optimized for different type of workload. We will dive deeper in 1 minute. Networking is also vital component in this space. We have a low latency network that has reduced jitter and also has very high bandwidth. And this is the, let's say, enhanced networking is what is more popular in HPC workload. We have also several different options for the storage, like EBS, EFS, and S3. Then we also have tools that will help you to automate and orchestrate your HPC infrastructure. For example, we have Batch, we have CfnCluster and Nice Engine Frame. Finally, we also have tools that will help you to visualize the results of your simulation. So instead of downloading the data, you can easily visualize the data where they are generated. So now let's dive deeper into these components. So let's start with the EC2 instances. On AWS, we have several different types of instances, and this is the different types, and the number of instances is always growing. That means that you really can select the compute that best fit your workload profile. So you should always try to match the architecture to the job and not vice versa. We have, for example, C5 instances that are compute optimized, or we have Z1. This is a recent addition, Z1 instances that these come with 4 gigahertz CPUs. We have instances equipped with NVIDIA GPUs, like the G3 for graphic intensive workload, or the P3 for CUDA code or for machine learning. But we also have instances equipped with the FPGA, like the F1 instance type. Storage. So for storage also we have different options. And these can be categorized based on the different type of infrastructure that we have behind. So EFS is our NFS as a service offering. So it's a managed NFS service. It is very convenient because you will pay only for the amount of data that you save on it, and so it's and we will take care of all the rest. EFS is not even if you can obtain very good performance on EFS, it's not really designed for high performance. You can use it, for example, in an HPC environment to save your home directories, or to save the configuration files of your application. But for example, for Scratch, the Scratch area of your jobs, you will obtain better performance if you can run on block storage. And for block storage, we have two different types. We have EBS and Instance Store. So Instance Store, it's basically it's like a local disk that comes together with your instance. With the Instance Store, you can achieve very good performance, but you have also to keep in mind that these are ephemeral. So if you don't save the data, when you turn off the instance, this will be lost. EBS is our standard block storage, and it's very similar to a network attached storage. So you can attach an EBS to your instance, and then you can mount a file system on top of it. So if you want, for example, to deploy a Lustre file system or another type of high performance file system, you can use EBS to build this type of file system. And then we have the object storage. The object storage is the most convenient, but is not POSIX compliant. So you can use your the AWS API to save data to our object storage. And this is basically is S3. But in S3 you can also manage the life cycle of your data. So you can easily move data from S3 to, for example, S3 infrequent access. That is more convenient, and then move data to Amazon Glacier. That is even more convenient. Basically, based on the duration of your data, you can move between Instance Store to block to S3 to Glacier, and this will help you also to save money while achieving the best performance. We have also several different options for data transfer. You can use Snowball, for example. That is an appliance that we will send you to your data center, so you can save all the data there and then move back to AWS. Or you can use Direct Connect or a VPN to upload data from your data center to AWS and vice versa. For high-speed networking, we have the Elastic Network Adapter. That is the latest generation of enhanced networking. It can provide up to 25 gigabit per second in a cluster placement group. And we have also open source the driver. So that means that you can, if you are running on Amazon Linux, for example, this is obviously is already configured for you. But if you want to run on Red Hat or other operating system, you can easily download and install the driver on your instance. It is compatible with MPI libraries, including OpenMPI 3.0. And it's also, in order to achieve the best network performance, it's also important to use a cluster placement group. So a cluster placement group is a logical grouping of instances in a single availability zone. And it's really recommended to use cluster placement group for applications that need low latency network or high network throughput, or both. Then we have the remote visualization. You can use, as I mentioned, DCV to stream the GUI of your application from AWS to your client in your data center. So instead of moving the data, instead of moving the output of your simulation from AWS back to your data center, you can use DCV to visualize the results, so to stream the graphics from AWS to your data center without moving the data. And this is obviously is very convenient. And if you have, if your simulation has generated very big data, this can also save you a lot of time. Then, in order to help you to automate and manage this infrastructure, we also have different tools. One of those is AWS Batch. That is a set of fully managed primitives. It basically is a job scheduler on AWS, and this will help you to focus on your applications. So your shell scripts, your executable, your Docker images, and the resource requirement. And in the meantime, we will take care of all the rest. AWS Batch is basically composed of the job definition, compute environment, and a scheduler. So you have to define the template for your job. This is the job definition, and the application that needs to be run, the job resource requirement, the role associated with your job. And then you have to describe the compute environment. So that is the requirement from a computational point of view. For example, the instance type that you want to use, the minimum, maximum, and desired number of cores that your application will consume. And you can also specify a spot price, for example, as a percentage of the on-demand price. And finally, we have the scheduler. So the scheduler basically will evaluate based on the job definition and your compute environment characteristics. It will evaluate where, when, and how to run your jobs to AWS. So you just define the environment and the job, and then you can start submitting job to the scheduler, to the job queue, and AWS Batch will automate the execution of the jobs for you. So another very interesting automation tool is CfnCluster. CfnCluster will automate the deployment of an HPC cluster on AWS, and it will also deploy for you one of the most popular job scheduler, for example, SunGrid Engine, Torque, or Slurm. CfnCluster is built on top of AWS CloudFormation, so it will automate for you the deployment of your computing nodes. And you can easily modify it in order to plug in your application and the libraries that you want to use. So what CfnCluster will do for you? It will handle the scaling of the computing nodes, so the auto-scaling group. So you just need to submit your jobs like you're doing every day. And then CfnCluster will look at the number of pending jobs in the queue, and it will automate the start or the termination of the instances on AWS. So the elasticity of the HPC cluster will be completely automated with CfnCluster. So now let's try to put all together in a single picture, in a single framework. So as you can see here, let's start from the bottom. Here you have your storage. This can be filled from your on-prem resources using Snowball or Direct Connect, for example. And then here you can have your shared file storage that then you can move if you want to S3 or Glacier. Then on top of that, you will have your computing nodes. And obviously, you want to benefit from auto-scaling, so that the number of nodes will vary based on the resources that you need and based on the number of jobs that needs to be executed. And you can use AWS Batch or CfnCluster to control this layer. Then you will have some other nodes that probably will be always up and running. For example, the head nodes or the license manager nodes. And finally, you can use DCP or Upstream 2.0 for streaming the graphics. So streaming the output of your simulation from AWS to your team client on-prem. Okay, so this is a summary of the different components, the different products that we have in order to help you to run your HPC application on AWS. Now let's see how you can, what you can do in order to choose the right configuration for your workload. So first of all, we can classify different type of HPC workload based on two main parameters. One is if the application is tightly coupled, so that if there is a lot of interaction between the nodes when the job is executed. So for example, MPI simulation. On the other side of the spectrum, we have loosely coupled or grid computing type of simulation. So jobs that are distributed among several different nodes, but these nodes don't communicate during the execution of the simulation. Another dimension is the data. So we have HPC workload that are more data light, so they have minimal requirement for high performance storage. And what we have also workload that are data heavy, so they really need very high performance type of storage. So these two dimension defines 4 different quadrants, and we can identify the requirement of the different type of application by position them into these 4 quadrants. So for example, seismic processing or astrophysics, these are usually tightly coupled type of workload that also are really data heavy. They need very high performance storage. CFD, computational fluid dynamics, it's also very tightly coupled, but usually is not so much data intense. On the contrary, risk simulation or molecular modeling, these are more distributed and are also data light. On the contrary, we have genomics or semiconductor verification that are distributed in nature, but need very high performance storage. So you can combine different type of solutions based on the needs of your application. And these, now coming back to the instances, this is probably one of the most important topic that we need to remember. In AWS, you don't have to select only one instance type. It's perfectly fine to have different instances for different type of workload. So you can really match the architecture to the job and not vice versa. And in the next slide, we will give you some example. So for example, M5 instance type is the latest generation of our general purpose instance. It is also available in the M5D version. When you find a small d close to the instance name, that means that the instance is equipped with local NVMe SSD storage. This is a local ephemeral storage that can deliver very high I/O performance. With M5, we have seen 14% price performance improvement compared to M4, the previous generation. And M5 is powered by an Intel Skylake CPUs. Skylake is the latest generation of Intel CPUs. On M5, the CPU clock frequency is 2.5 gigahertz. Like all the other instance type, M come in different sizing, and the largest one has 96 virtual cores and 384 gigabytes of memory. So you have a ratio between memory and virtual CPUs that is 4 versus 1. Skylake CPUs support AVX 512. AVX is an extension of the x86 instruction set for doing single instruction, multiple data operation on Intel CPUs. So for vector and floating point workloads, AVX can twice the performance for your application. So it's recommended to use a version of the application that support this new instruction set, or if you can compile your app using AVX 512. Now, talking about use cases, our customers have seen very good performance for finite element analysis, for implicit finite element analysis, for example, on Abacus Implicit. So if you want to run implicit finite element analysis simulation, you should give a try to the M5 instance type. Then we have the new generation of our memory optimized instances that are the R5. These come with more memory on every single instance. So the ratio between CPUs and memories is much higher, is 8:1. And also in comparison to M5, the frequency of the CPU is much higher. Here we have 3.1 gigahertz. So this is really optimized for it is really memory optimized. So it's very useful for example, high performance database or big data analytics. Also, finite element analysis can run on R5. And by the way, R5 also comes with a R5D type. That means that you can have up to 3.6 terabyte of local NVMe storage on a single instance. Then we have our compute optimized instance type. The latest generation is C5. And also C5 is available with the D, so with the local NVMe SSD storage. We have seen a 25% price performance improvement over the C4. So this is a really significant price performance improvement compared with the previous generation. C5 is based once again on the Intel Skylake CPUs, and it based 3 gigahertz CPUs, but it can run up to 3.5 gigahertz using Intel Turbo Boost technology. The ratio of the memory per core is much lower in this case. It's just 2 gigabytes for every virtual core. And like all the other Skylake instances, it supports the Intel AVX 512. We have seen very good performance when using C5 for CFD simulation, for example, on ANSYS Fluent, and also for explicit finite element analysis. Then we have instances equipped with NVIDIA GPUs. We have the G3 for graphic intensive workload, and then we have the P3 for compute workload. The P3 are equipped with the NVIDIA Tesla V100 GPUs. These are the latest GPU available on the market. And that means you can have up to 1 petaflop of computational performance in one single instance. So if your application, if you can run CUDA code, if your application can benefit from use CUDA, so if your application can benefit from GPUs, this is definitely the instance type that you want to use. We have seen a 14x performance improvement compared with P2 for machine learning use case, and a 2.6 performance improvement for HPC use cases when compared with P2. So P3 is recommended when you have to run machine learning or artificial intelligence type of workload, or when you have to run CUDA code. Then we have the F1. F1 is the first cloud instances equipped with FPGA. As you know, FPGA can speed up application up to 30x. We provide also tools to develop, simulate, and debug your code. Then you can package it as an FPGA image, and then you can use the F1 instance using the image that you have saved before. Very important use cases are financial computing, genomic sequencing, or image and video processing. So in this use case, FPGA can provide a really significant improvement in terms of performance. Then we have Z1 that is designed for high frequency compute workloads. This is a brand new instance family. It's been released, I think, 1 or 2 weeks ago. And this is also the fastest one. The CPU frequency is at 4 gigahertz. So this is the fastest of any cloud instance. And it is powered by a custom Intel Xeon processor. We have, in this case, 8 gigabyte per core. So it's there is a very good density in terms of memory per core, and it also is equipped with with local disk with the NVMe interface. In this case, it can be up to 1.8 terabyte of disk. So Z1 is really designed for high compute performance, or for example, all the cases where the high per core licensing is very expensive. For example, electronic design automation is a very valid use case for the Z1 family. So in this table, we have tried to summarize what we have seen in the previous slides. For every instance type, we have reported the CPU clock speed, the number of cores, the size of the memory, and the size of the SSD storage when it's available. We have also included some examples of typical use cases. Please note that except for T instances, each vCPU on AWS is an hyperthread of an Intel Xeon CPU core. So if you want to run your application without the hyperthreading, you can calculate the number of physical cores by dividing the number of virtual CPUs by 2. So this table is reporting also the number of physical cores and the the memory per physical core ratio. In the table, we have also included the C4 instance type, because we have seen that in some cases, also the previous generation can deliver good price performance for CFD applications. Okay, so these are the recommendations that you can try to follow in order to select the best instance type for your workload. But then there are also other tuning that you should take into consideration in order to get the best performance. For example, for tightly coupled type of workload, you should always use cluster placement group, because cluster placement group is an option that will reduce the latency, the network latency, and so they will accelerate the communication between the nodes. For the same reason, you should also enable enhanced networking, as we have described it before. We always recommend to test your application using Intel MPI or OpenMPI 3.0 and make use of all the available tunings in order to optimize your MPI code. It's also important to choose the right number of cells per core in order to improve the per core efficiency. For example, there was a blog post in the ANSYS blog that you will find the link later. And ANSYS has run a very interesting benchmark of Fluent on AWS, and they have found that if you can stay above 50,000 cells per core, you will get the best performance on AWS. Finally, if you want to test your application on AWS, we recommend to use real-world example. So do not benchmark scalability using only small example or a synthetic benchmark. There is really no value in this type of test. It is always more interesting to use the data that you are using in production, so real use cases, in order to understand if the application would run well on AWS. Then for all the other type of workloads, of HPC workload, is always recommended to use Amazon Linux, or if you cannot use Amazon Linux, use an updated kernel, for example, the version 3 or higher, 3.1 or higher. If you want to use NVMe, you have to use kernel version 4 or higher. As we said before, it's recommended to select your instance type based on the previous recommendations. Feel free also to try different instance type, different applications, different type of different inputs can perform differently on different instance type. So feel free to also experiment with different instance type. It's also recommended to use p-state to reduce the processor variability. And then hyperthreading is turned on by default on AWS. In many cases, in HPC, there are no real benefit on having hyperthreading turned on. So we recommend to test using hyperthreading on and off, or let's say use the same settings that you're using on-prem in order to achieve the best performance. In the last slide, you will find a link where is described how to change the p-state and disable or enable the hyperthreading on AWS. Okay, so now let's jump to the next topic. We will share some use cases, and then we'll come to the conclusion of this webinar. Let me first tell you that we have also a very large set of partners that are helping AWS to succeed in the HPC space. Here you can find just few examples of those partners. Intel and NVIDIA are obviously very important for us. All the AWS instance type are powered by Intel CPUs. And as we have seen before, we have also two families, the G family and the P family, that are equipped with NVIDIA GPUs that are now widely used also in the HPC space. Then we have very good collaboration with software vendors for job schedulers, for example, Univa Grid Engine or Altair PBS. You can find them in our marketplace, so you can easily deploy a PBS cluster or an Univa Grid Engine cluster. Then we have collaboration with ISV, for example, ANSYS is one of the most popular on AWS. And we have also a number of system integrators that can help you to run your HPC workload on AWS. 6nines is one of those. Finally, we have also some partners that have built their own offering, their own HPC as a service offering on AWS. Rescale is one of those. If you want to try, you can go to the Rescale website, and literally in just a number of clicks, you can select the application you want to run, upload your input, and they will do all the magic for you. They will start the cluster on AWS. They will run your simulation, and when it's done, you will be able to download the output. Now, coming back to the use case, this is very interesting. This is Clemson University. They have been able to run single simulation that have used more than 1 million virtual CPUs. So this is massive. Obviously, it's probably one of the biggest job in history, and this has obviously it has been run on several different availability zones, and using spot instances. So this is, I think, a very good demonstration of the capacity of AWS to scale without limits. And so to enable completely new type of workload on AWS, if you want to run HPC on AWS, you can really start thinking to do something that was not possible before in your on-prem data center. The next one is this is a real Guinness World Record that has been set by the Children's Hospital of Philadelphia together with Edico Genome. So they have used our F1 instances, so the instances equipped with FPGAs, to run a number of genome analysis, human genome analysis. So they have been able to run 1,000 pediatric genomes in 2 hours and 25 minutes. This is an incredible acceleration, and you obviously, it's very easy to understand the impact that this can have for a researcher trying to bring precision medicine into the mainstream clinical practice. It means that you can have the results of your analysis in just a couple of hours. Then we also have an interesting use case in the financial services. Aon, for example, it's a customer who needs to run their Monte Carlo simulation using a very large number of GPUs. This is obviously very expensive on-prem, and so they have decided to move their infrastructure to AWS, and they have deprecated their co-located data center. And they're also said that we've been able to reduce one of their process from 10 days to 10 minutes. So this means that it can be as much as 500 times more efficient in terms of performance per dollar. This is, I mean, is not only saving money and bringing elasticity. In this case, there is a clear business advantage or competitive advantage in being able to run simulation, complete a simulation faster and faster. Okay, so now let's try to summarize. Basically, HPC on AWS will allow you to fundamentally rethinking what is possible. So instead of worrying about your capacity, instead of worrying about the number of jobs that you have in your queue, you no longer have to worry about the technology behind or the refresh cycle, because you can benefit from the AWS space of innovation, and you can, when a new instance type becomes available, or when a new GPU types, for example, becomes available, you can immediately start benefiting from it. You can you don't longer have to worry about your upfront investment, and you can easily collaborate with your colleagues or your partners all around the world, because you can easily spin an HPC cluster on every AWS region all around the world. So the idea is that you can now stop worrying about all these things and start focusing on your application. You can have your researcher, your scientists, your engineers being focused on innovating, innovating your products, your business, instead of being focused on the IT technologies. So these are a number of further reading. If you want to dive deeper, we have white papers, we have our HPC reference architecture. There are also a couple of blog posts that I've mentioned before that you can find useful. So thank you very much for your time. It's been a very great pleasure for me to have this webinar. And now I'm ready to answer your questions.